want to understand what is the physics.
Pushing is, I took some old calculation I had done many years ago, 30 years ago, using the Vlasov dynamics. So Vlasov dynamics is essentially time-dependent at Fock, but in phase space and some semi-classical limit. And in order to go below the Coulomb barrier, we use a technique which originally was suggested by Feynman. It's also called Feynman path integral, but essentially we do the physics in imaginary times. I will explain you what it is. And this was a long time ago. More recently, we are trying, since I start to like again, trying to use instead of Vlasov constrained molecular dynamics, which is now a many-body problem, while this is a mean field, so does not have any clustering like alpha. And so while constrained molecular dynamics can give us clustering, not only with this, I could do even proton nucleus, while with the mean field, I had to have average nuclei of mass larger than alpha particles. And so, but first, I tried to, together with John Atowitz, to see how we got involved in this. Instead of using already this very complex codes, which I also lost in the last 30 years, so I don't know where they are. Probably in some VAX machine, if somebody of the older people remember what the VAX is. And so we started with an even older model, which is a neck model, which is a macroscopic model, which assumes a well-known potential, like the bus potential, which I was using here. Coulomb is well-known. And also, yes, the possibility the two nuclei to touch and make a neck, and the neck will act like a glue between the two nuclei and allow for exchange of nucleons, which gives some friction. So this was well developed, and we tested, and I showed some results. And then I decided, well, the best thing first, instead of getting involved in these things, also I didn't have a student, now I have a student. It was to use this model and extend to imaginary times. So this was always developed above the Coulomb barrier. With going into imaginary times, we can go below the Coulomb barrier. And we use some tricks to include resonances. I will, if there is time, I will discuss about the possibility that in this subbarrier fusion reaction, there is some pair production, which could increase the probability of fusion at low Coulomb, at low beam energies or low relative energies. And then I'll try to conclude. So the paper I'm referring was published in 2020, was collaboration with John Atowitz. So we are under COVID. We are both in Texas. It was winter, so essentially we were keeping us company. And we had some discussion coming from this paper by the Catania group, which used the Trojan horse method, which already was discussed yesterday by Marco and the other people I mentioned. Originally, I guess was this the publication. And at the same time, another paper came out a little bit later, not exactly the same time, by Akram Zanov. So the nice things of this, I was somewhat, so I was first at LNS, so I know all these people, but I'm also Texas A&M, so I know all these people. And we just say, oh, they're fighting, so let's get into the game. And the reason of the fight is about this astrophysical factor, which is defined here. This is a star, just a reminder what it is. And there was this plot given by Akram and collaborators, where there's this S star as function of E, and direct data are this oscillating curves. And then the Catania group with their Trojan horse method got this part here, but Akram say, no, there should be some hindrance and it should go actually this way. So here the difference between the two results is order of magnitude. The other thing that interested me is this.
You have repeated just to guide the eye.
Which one?
The experimental flow energy. The true values are the ones which go up. So?
No, these are the true values according to her. These are the true values according to Akram.
Yeah, but just to put a correction factor, you didn't put any resonance.
The resonance
No,
at the
but the experimental values are
Up,
up.
black ones.
Okay.
But what is the dashed line? It's
Pull down. So the true. So do you do a triuniverse method? Then you assume something, and this let me think, maybe this something was assumed by these people here, and they got this data. But Akram, just a moment. Akram told them no, there should be some Coulomb correction. I think Marco discussed this yesterday. Some Coulomb correction because you are using nitrogen 14 in this thing here, and this Coulomb correction in reality will correspond to a smaller phase space. So it should go like this, and so the resonance are not up here, like she says, but they are down here. Is this the right?
But we don't know where they are.
We'll get there.
Okay.
So, but this was the situation at this time here. But you can see already some models. For instance, this is a couple Charlotte model. They will give you this kind of thing. They don't have the resonance, but they will clearly tell you that if there are resonance, they have to go above this. But there are other models like this hindrance model, which Akram was referring to. They will give you this kind of things here. So you asking me what is this?
Yeah,
You should ask Akram. I don't know. It's this figure. I don't see it. It's dashed line. I don't know what it is. It looks like following this trend here. I think it's following this. But the other thing that interested me were this oscillation in the direct data, which we had predicted 30 years ago. So we're able to finally experimentalize this. So the paper I'm referring to with the mean field is this paper here, where published in '94, and this is for the fusion of carbon on carbon. There is some paper on the same using the same method for fission, so I'll give you as for reference if somebody is interested. So what you do in this case, you solve the Vlasov equation in imaginary time. How do you do this? Is you have to define some collective degrees of freedom. So you have to know what your major degrees of freedom in subbarrier fusion are. And here is for carbon on carbon, for instance, it's just what we chose was the relative distance between the two nuclei. So those you can get microscopically from solving the Vlasov equation. The Vlasov equation will give you this phase space distribution at each time step for each R for each P. So if you multiply this by R and you integrate over the phase space on region A, so you have the center of mass, the two nuclei on the two sides, one is side A and one side B, you get, and you do the same for side B and take the difference, that will give you the relative distance between the two nuclei. And you can do the same for momenta, you get the relative moment. And if you put the Vlasov equation and you solve this, you do the time derivative. So the collective momenta is going to be the collective velocity is going to be the momentum divided by the mass, while the collective momentum is going to be the force. But just Hamilton equations. So this is nice until and it's completely classical. But if you have a barrier, of course, when they get to the minimum approach, they will go back because they have a Coulomb barrier. So what you do there, you go into imaginary time. So you go from T to I tau. Why you do that? Because the collective degrees of freedom now, since the momentum is a derivative with respect to time, the momentum becomes imaginary. And when you do the force equation, you get twice the derivative with respect to time. So you get a minus, you get I squared, which gives you a minus. That means your force becomes negative. So it means if you have a Coulomb barrier that is pushing your nuclei back, when you get to this point here, you got imaginary time, and the Coulomb force becomes attractive, and you go in. So this is the method, and it's used in many fields. And this is the result for carbon on carbon at this energy. So the two nuclei, so this is the phase-phase distribution. Here is the density distribution at time t equals 0. And we follow in time. So the energy is below the Coulomb barrier. And around 300 Fermi over C, they get into the first turning point. So at this point, you go to imaginary time. And as you can see, imaginary time, the two nuclei get accelerated. And again, they get inside the Coulomb barrier. And when they get to the nuclear force is attractive in real time. By imaginary time, it becomes repulsive. So they stop. So at this point, they stop. Then you go back to real time. And what happens is that they continue they are already inside the Coulomb. They continue their dynamics, they make an egg and they fuse. So from here to here is imaginary. This is the real time. This, of course, was real time. So the important things in this case, you have to calculate the action, because the action gives you the probability that these things happen. And so what happens here is you started so this is P calculated in this mode, is the relative moment of these two nuclei as function of the distance. And at the beginning, they move under the Coulomb trajectory and they get to the first turning point. Here, what happens is you go to imaginary time, so they get accelerated by Coulomb. And this forms the two nuclei that they go towards each other and they accelerate, and they develop these oscillations. Then when they get very close to each other, and here depends on the equation of state that you are using, they get stopped because of nuclear force. They like hit a wall, and they stop at point 2. After this, you are back to real time, and they just starting oscillating, and that means they're fused, which is what you see here. So now, if you calculate the area that is in this region here, this area is the action. E to the minus the action of here's in units of h bar gives you the probability. And then since you know what impact parameter in this case was 0, but you can do for different impact parameter, you can calculate the cross section. But the important thing that you see, there are a couple of important things. One, you start seeing the strange oscillations. So if there is life in imaginary time, you should see this oscillation in real physical observables. And when you calculate the cross section, you see this oscillation to be reflected in the cross section when you do a function of the energy. So this thing here gives this oscillation that, as I showed you before, were kind of seen in the data. And at that time, so in 94, astrophysical factor was not so popular. So we didn't do that transformation to S. And the other thing that we didn't do, we didn't think the experimentalist will go below 2.5 MeV. So we stopped the calculation there. So now that's why we're starting to do this calculation to go much below. So this is
this trick of going to the imaginary time is not the same as in quantum mechanics having a tunnel, right? Because the tunneling is like a wave mechanical thing, and here you still have a classical mechanical.
Yeah.
Did you ever compare for simple barriers?
Yeah, Feynman did.
Feynman did.
Yeah. So and it works. You can do yourself. It's and it works very well. Here, of course, is much more complicated because there's nucleons. They start moving, and then you get this strange thing oscillation.
And you also have many body here, right? So you have these densities there.
As many body, but we are doing mean field, right? So So that means I have some symmetries that I have to
And
respect.
probably what Feynman did was something much simpler.
Tunneling the of a barrier, harmonic, some harmonic barrier, and so on.
You have actually thought, so do you have single particle degrees of freedom?
Yeah, this is the single particle degrees of freedom. Interaction, so the nucleon, the particles are interacting through a mean field,
But
which
in
was
the
a
end,
Scherm
it's
interaction.
a surface effect that makes them misusable or not.
I'll get there. In this case, they arrive to this point, there is no neck. See, and yesterday there was a discussion about neck and so on. So there is no neck for this, but when I'll show you some heavier nuclei, you will see that there is a neck. So it's a surface effect. Yes, the surface, the nuclear force comes here. And there's a region here.
Okay.
And there is another question that Jack asked yesterday. And also this is somewhat connected to the microscopic model that I'm showing later. Is what is the Trojan horse measuring? Trojan horse is not measuring this, it's measuring what happens here on. So it's measuring what the compound nucleus is. And this is something, assumption that I made based on this result when I show you what I'll do for the microscopic model to add resonances. So having this, I can show you some other result and maybe answer a little bit the question. This is oxygen and oxygen. So we did this a few years later. Here's the paper. Oxygen. Here you have the mean field as function of the different x and zeta plane, for instance. So this is 12. Here's the relative distance between the two nuclei, which I described before. Minus 2.8 is the time. 0 is the time where you enter imaginary time. So this is the time before entering imaginary time. And here's the density distribution of the neutrons at different contour, so like 1/3 and so on. So for oxygen, we have similar feature like a carbon on carbon. So that means the potential at this point, they are quite well separated. And when they enter again, so here imaginary time, and here they get into real time. There is not real and neck formed. On the other hand, if you do nickel and nickel, which is a much heavier system, you enter imaginary time here, and there is already neck. So the physics between this and this is completely different. And this is discussed somewhat of a speaker yesterday that was saying about hindrance effect. So hindrance effect in this model will come for heavier nuclei, and they will be given like, and for this case, for nickel plus nickel, by the fact that you are making a neck. And the neck will then give you some exchange of nucleons, and this exchange of nucleon is some kind of called known as a one-body dissipation. So no nucleon collision, because in this case.
Question. So for the oxygen, this is the calculation for 8 and 11. So if you just decrease the energy, the situation should be even, I mean, the no neck at all, because
They will come alive far apart here. But here they may get to the same point. The action will be large. So always you have to call so this was the result for this paper, which is published, I think, in 2000, for our cross section and experimental data known at that time. This is oxygen. This is a nickel on nickel, 58, 58, 58, 64, and 64, 64. So far so good. So I had this experience, but we're in this place, and I'm not going there. So what we are doing now is I got a student a few months ago, Theo de Pastas, and he's working very hard to use, instead of using a mean field, and now we're using a molecular dynamics. The difference here, I can make clusters. And the constraint is somebody yesterday mentioned anti-symmetrized molecular dynamics. This is similar to that, but here we put a constraint which keeps into account the power blocking. So this thing is numerically very easy, very fast to do. And at each time step, your phase space distribution is always fulfills Fermi-Dirac type of distribution. So it's a system of fermions. So these are very preliminary results, possibly wrong. I wrote very small, so you don't see it. And so the blue are the protons and the red are the, and this is beryllium 8 on beryllium 8, so you cannot do it experimentally to prove me wrong. Of course, you could invent a double Trojan horse method. You ask Mr. Akram to solve your equation, he gives you an equation of 75 pages, and after a while, you get the result also in this case. But so this time I'm going to put the cross section and I'll go to 0. So if you do that, and so here you can see here already fused, but you didn't see the part where it was entering into imaginary time with such an action. So here we are still working on, okay, started all over again. And at some point, here the difference between the mean field where you saw the spherical object is completely, so here your imaginary time.
Sorry, can you do a mean field for beryllium 8, such a small nucleus?
Yes, think of beryllium. Yeah, they cannot check me experimentally, so why do you care? But with this method, I can do proton on a nucleus, and I could do alpha particles. Of course, you have lots of work to do because you want the binding energy of alpha particles to be correct and so on.
What is constrained in this?
Constraint is you force your phase space distribution to fulfill the Pauli principle. So these are fermions.
Okay.
So if I do molecular dynamics without the constraint, I get Maxwell-Boltzmann distribution. If I do this, I get Fermi-Dirac.
But these are like wavelets, like little waves, or what are these?
So each nucleon is a Gaussian in phase space with the given width. Here, the width is much larger than the dimension of the point. But you have to imagine this Gaussian that are moving, and the centroid of the Gaussian is what we are plotting here. So, and of course, how do you get to mean field using this one? You just make thousands of events and you project on top of each other.
And then you get those.
And then you get this stuff. Now, this is different from Vlasov because here there are no symmetries. Of course, when I do averaging, you may get some kind of symmetry, but each one of these is an event. So for instance, this guy, this neutron was oscillating back and forth, or they may enter in imaginary time at different times and so on. Or at the final state, you can see maybe an alpha particle is making at the surface in a particular event, or a neutron is escaping here. So it's much more ambitious, but I'm retired, so who cares?
Oh,
The student is the problem.
But
I have to give him a PhD.
what prevents each of these Gaussian wave packets to spread?
That we don't have that. So,
What?
so if they escape the thing by a spread,
Yeah.
and people who have tried this Japanese putting this as spread, it didn't work so well because they will spread so much that they will see the nucleons that had abandoned and they will go back where they were. So you go towards the mean field, the description if you do that. So here the width is fixed. But in any case, we are doing compound nuclei. So fragmentation is a little bit more probable, but this model was made for fragmentation and works very well there. So am I going back?
84.
So I go back to 84 when I was a student of George Besh. So this is because, as I say, we were confined in Texas with Joe, and there was this fight and say, I cannot do this microscopic model. I can use this macroscopic model. So macroscopic here means I have two nuclei which are described by point particles or something like that, and they interact to a Coulomb force and a bus potential. So a phenomenological potential. You could use M3Y potential, which is folding similar to what Angela described. And at some point, if the energy of the beam energy is good enough, they can touch and make drops, which with the surface tension with the two nuclei, and they fuse. So the original idea, which was George's idea, then I was a student, is he wanted to fit time-dependent artifocal results with the simple physics, which we did, for instance, for this case here. So this model has been tested above the Coulomb barrier. This is for fission, California 252. The experimental data are actually the full line in this case, while the calculation of the points. So we don't have a shell effect here, this breaking into some asymmetric kind, but the kinetic energy is well described. Another thing is the Wilczynski plot. For instance, so this is the result of the model. These are experimental result, and this is a neon on neon above the Coulomb barrier. So this is what I did. This is a program that essentially is 200 lines. So it was easy, even if I hadn't done a Fortran for years. Even I could repeat this. Of course, I lost all this program, so we had to rewrite, and we did. And what we did is got imaginary time to go below the Coulomb barrier. What's next? So for each, as I said before, now I give the formula. The probability is given by this, for each L waves is given by the action. 1 divided by 1 plus exponential to A. Sorry, there is this thing in front of it. And A is the action, P1 star delta.
With the mouse, I think you can move this to the bottom.
Which mouse?
Mouse on the computer. No, yeah, go to this black stuff
The
there.
mouse is scared of the cat. So, and if I'm out,
Yeah.
so to take into account, so she was bothering from,
Anyway,
How
because
many
we are
times?
presenting, so.
yeah, it doesn't work. She was buying, why don't you put resonances? So what we did is, okay, we can put a resonance. The only parameter we can touch is the bus potential. So we say, okay, the bus potential can be modified because you have resonance in the compound nucleus, like we had shown there in the previous transparency when I did the Vlasov calculation. I said the Trojan horse, they can see all of the compound nucleus. And that means we can increase the bus potential by a Gaussian or a Lorentzian, which has the energy of the resonance of a particular state in magnesium 24 with a given width. So if you do that, and so the information that you need to do to give it here is the values, the L value, the position of the resonance, and the width of the resonance, so the natural width. So this we take from the literature, and the rest is the same, exactly the same model. So now it comes S star, the green line is our model, and here there are different L values. So let's say this region here, L equals 0, then L equals 2 start to be important here, and so on. And adding this term gives you these nice peaks, which more or less correspond, actually, more than less, correspond to the one that the Trojan horse. So the two methods were, thank you. And the other nice things is Vlasov. This is the Vlasov equation that I had solved many years ago. She actually took the point from the publication and derived the S factor, and I thanked her. And so this is our oscillation from the Vlasov. So this is another calculation. And this, of course, are the experimental data that have been discussed. And this is still the result from Akram. So this is one thing that here was curious. I have this oscillation here. Say, oh, what about it? And I stopped here 2.5. So what about this guy decided to go like this? That's why I'm repeating but I think it's going to be something like that, but we'll see. So now since I have this model that is working with my previous student, which now is in China, he got a student which is called Shooting Sun. This is her name. This is her name. And I said, why don't you do this for oxygen and oxygen, including the resonances. So the experimental data are here, L equals 0 C, and now the situation is different because Q value is so large in this reaction, and the resonance are at a large value of L. So if you put the various contribution at 0, 2, 4, when you start seeing the resonance, they're much more below this guy here. So Trojan-Horse method, please put your points now. Now I went to 0. So now you're not going to trick me. And carbon plus oxygen 16. So in this case, I'll make a little bit bigger place. So this is experimental data. And when we do this without resonance, we get this. I thought this region here looks like these two bumps here. You see the might result in these two bumps here. They look very strangely close to where the giant resonances are. So we had the giant resonances we got here. We had the resonance for the whatever it is, silicon 28, and we got this one. So we don't get this actual structure, but we get this increase. Do I still have time? Are you tired?
So you have 5 minutes.
5 minutes.
Plus 5 minutes is good.
So, okay, since I have 5 minutes, I'll discuss something that another student of mine, Thomas Settlemire, is doing. So this is actually it's a talk. I just copy and cut. And here we were interested more in another aspect, which is screening. Some people say, some results, I say that there is screening in the infusion of light nuclei, which could be above the adiabatic limit. And we had done some work in the past, and we couldn't find with the electrons, constrained molecular dynamics, but with the electrons going around this nuclei, and we couldn't find any reaction that will take us above that adiabatic limit. But there could be another way to go above it if there is a dynamical production of pairs, so a plus and minus. So what do we do is, let's say, if we follow the dynamics like in the model I've showed you before, could be the microscopic or the macroscopic. And for each distance, relative distance between the two nuclei, we solve the Klein-Gordon equation. Essentially, is the Dirac equation, we are neglecting spin-spin interaction. And if you do some manipulation, you can get a Schrödinger-like type of equation. Essentially, you divide this by 2mt. Mt is the transverse mass of the pair that you want to produce. And this will be like a Schrödinger equation under an effective potential. So you started from the real potential, you define an effective potential, and you get a Schrödinger type of equation. Effective potential is given here, where Mt is the transverse mass of the particle you want to produce. And here, for instance, for electrons, the transverse mass would be the mass of the electron plus the momentum in the direction perpendicular to the direction where the two particles are tunneling. So what you can do is that negative energy particles can tunnel through this effective potential and become real. So this might be nice or not nice, but you can think of some geometrical type of model, the description, where you have the two nuclei at a given distance r, and your pair is essentially you're going to create it over here. And now what you can imagine, you can calculate the probability. Of course, there could be other configuration, but you can calculate the probability for the positron to tunnel and get emitted here. So if you are in this kind of situation, now the electron is in the middle of the two guys, and it gets and it can create it lowers the Coulomb barrier of those two guys. So that means they can accelerate and go easier in fusion. Of course, you have to spend the energy to create the pair, but the cross section will go down so much that the energy that you spend on the pair could be well spent. So this is did somebody say so?
If you use this vacuum polarization potential, the effect is stronger than that.
I'll show you.
Are you sure?
So But I'm not giving the talk for you, I'm giving for the experimentalists. I want them to measure this. And if you decide to measure, don't look for electrons that have to have the same energy of the positron, because this method means the electron is going to stay here to attract those two guys. The positron is a Coulomb charge that will repel it. So the positron kinetic energy could be completely different from the electron because they are interacting. So what does it mean here? So this is an example where of this diagram that I showed before. So this is the potential energy sent by the positron. So this is the part of the Coulomb between the positron and the two ions. It's all symmetric because I'm doing symmetric nuclei. And this is the attraction between the electron and the positron. We are putting a term here, which is the screening. So this will avoid that when the two guys are on top of each other, this goes to minus infinity, and you could produce energy from, you can produce particles, pairs from nothing. So this is a parameter of the model. And what we are assuming here, and this is the experimentalist could fix this parameter, is that when they're on top of each other, this term is minus 2mt. So that's so we are assuming a screening, which is essentially due to the energy conservation. You cannot go below this value. You have to have energy in your Coulomb field that has to be larger than this 2mt in order that you can take the particles out from the vacuum. So it's not just a study of fusion, but it's also a study of the vacuum. And we can do because we can produce very high fields. In this case, I'm doing carbon on carbon to show you the effect. So if this is your potential, then to this you have to subtract or add the mass of the transverse mass. So in this case, the transverse mass I'm assuming is the mass of the electron or the positron. So if you subtract, you are in this dashed line. And if you add, you are in this long dashed line. So in order to produce the particle, when they are here, they have to tunnel. So they are in the negative energy state, they have to tunnel and go into here. This is the condition that you work with this Schwinger mechanism that gives you the possibility of tunneling and to create a real particle. So they were to be essentially below this region here at 0 and tunnel. This particle is already above, so this is unphysical because it's not emitted. The particle is already outside of this barrier here. So that means if he's there, it has to be there for other reasons. So this is the limiting case. All the cases where this V effective at the point at 0 are negative will give you always this kind of solution. So this is how your effective potential will look like. So you can imagine your positron being trapped here, going back and forth, and then finally tunneling. For this case, it's not physical for the given mechanism I'm assuming. So if this is true, you can calculate the probability with the usual cross-section formulas, so the L values and so on, with the probability that you got from tunneling, and some probability which is due to the fact that you need to, the two nuclei are moving, so they will move in a certain time t, and then that time t, the vacuum is going to rearrange. So you need to, in order to calculate is the probability that is the process is going to happen, and that time you assume a characteristic time which is given by the Heisenberg indetermination principle, h bar over 2mt. So if this happens, you produce the couple, the pair, and you can calculate the cross section, and the final result are plotted in this way. Remember, I have one parameter. So this is fixed because of the parameter I told you before. So if experiments come someday and tell me that cross-section is much smaller, that means the vacuum that we were assuming, the screening is not correct. We have to have a larger vacuum. And so these are done as function of the relative acceleration of the two nuclei. So if the acceleration is 2me, twice the mass of the pair, then your cross-section starts from about 3 maybe, as a maximum and then comes down. So this is the probability of producing this pair. If you want the acceleration to be 4 ME, you get this red curve and so on. So that means, in our opinion, that if you get this kind of probability and this will be the right values, then creating a pair will be an easy way to overcome the Coulomb barrier. So experiments in this case should be an experiment that has a coincidence. So they have the pairs and singles. So just you measure how many pairs you want and what is their kinetic energy. And pairs that are in coincidence with the fusion fragments, like alpha particle if you're doing something, and then you make a correlation function. And that will tell you if the cross-section or one of those oscillations that we saw before in S star are affected by this kind of process, and which will depend, as I said before, from the screening. I'm concluding. So, okay, to what I told you, you saw before, so if I add the resonance on this kind of model, I get good agreement with Trainer-Horst method. This is the L channel equals 0 is dominant. For every system, resonance are not giving me too much of peaks. And thank you for everything.
Yes. So in the carbon 12 case, you actually had like a small hint of hindrance, right, as you go to the center of mass, lower center of mass.
Then S, that's S star, not S.
Right, but it's still a small amount of hindrance, right? That's
This is
carbon 12 case.
Carbon 12.
Did I pass? No,
Oh, you go back.
I passed the carbon 12. Okay,
You have to go back.
forward.
Forward.
Come on.
Yeah, right. So your green line is.
You mean this?
is hindrance, yeah.
This is entrance.
Yes. So do you understand that effect?
No. You mean I have a maximum here. This is S star, not S. So I don't know if S will be more pronounced, and then you may be right.
Yeah, but it should start like from 6 MeV. It looks like more like affected due to the Coulomb barrier. So 6 MeV means the barrier. So I need to start to have this slight decrease. I don't think it. So the hindrance, if I'm correctly, for the carbon is expected around 2.5 MeV, right? Something like that. So you should observe something like that, and then.
You mean this?
Yeah,
No, I think we should look at the other figure. No, what I'm thinking here is when you do S star, you multiply by this number 0.46 E.
So it's somehow changed. It's not a constant factor.
So what I told my collaborator for the other case is why we're using 0.46 for oxygen. Increase it until this becomes constant. So I think it could be that 0.46. I have to make it constant. So if I want to see the thing you are saying, maybe I should look at S, not S star. And I think that's what they do, the speaker of yesterday. That's what I think. Not.
If I understand well, your calculation do not agree with the data at higher energy, no?
The-
Much higher.
This part here.
Yes, I mean.
The Vlasov, yes.
Don't fit at all.
The Vlasov fits well.
It's the red one.
The red one is the Vlasov. The green is this model here. So let me say, so the Vlasov is the one microscopic that we did 30 years ago. That's the one where we spent some money. This was free. It's a macroscopic model, and this is the result. But then when I looked at this one, oxygen plus carbon, oxygen, and oxygen plus carbon, it works very well. So I'm not so sure. Before I look, I don't have too many parameters I could change because it's fixed from reaction above the Coulomb barrier. So I'm not sure before I change anything if my experimentalist friend.
Even the green line is.
Yeah, the green line is below that. That's what I'm answering. The model gives this green line is a little bit higher. Yeah, but my professor Birch told me, how do you think they do the experiment? And since then, so I don't have free parameters. So this is the result. With Vlasov, it works much better. And they're independent because the calculation was done 30 years ago. So here I could work again with use the proximity or something. But I don't know why it doesn't do the same for oxygen.
If you add in resonances that higher center of mass energy, can they negatively interfere with the green line? Or is it-
I had all the resonances which were compatible with the L values of the calculation are all there.
above 3, I mean.
Yeah, that the effect is too small. Similar to what I show here, the effect is too small. So that's I think in this case something was showing here, little peaks, but nothing really serious.
So coming to this E plus, that is impacted because of there. So it looks like if you go, anyway, if you go, let's say, at the astrophysical region, it should not play a big role. So it is very helpful to start going below the barrier.
Well, the reason why I do below the barrier is because this way is purely Coulomb trajectory. Okay, so I don't have problem with the nuclear field and so on. And the L values are also very small. So, and that's gonna give me, if not an enhancement of the fusion cross section, it's gonna give me a signature of the dynamics below the Coulomb barrier, if any. So that's and the other things I'm not talking here. If you do fission, is even worse. You can get E plus, E minus up to 30 MeV. So it's, if I'm not wrong and you are an experimentalist, I'll put some money on this.
Yeah,
You can put the money on the Hungarian experiment to prove that they are wrong. And then with the detector, what do? You prove me wrong and say, okay, does it work even for you? But there are no resonances here. It's just, I think carbon on carbon 6 MeV. That's what.
Why not have your nuclei?
Then you produce even more. That's what I'm saying. Fission, but fission. So you can do calcium, you can do uranium and uranium, but if you do fission, even spontaneous fission, I have a big source like that argon. You can put a detector there. Actually, we have one that we use with the laser. And look at if you have muons. If you have, sorry, you could produce muons, but if you have positrons, and say if there are positrons, it's a very interesting effect. We see that we can follow the dynamics of the positron of the model that we have from the positron production.
But I have a question. If you produce virtual pairs,
These are not
the vacuum
virtual.
polarization, these are not virtual, but there is the vacuum polarization, which should be a bigger effect on the barrier. It will change the potential a lot, right? This
No.
wheeling potential, you know this, right?
Yeah, we did this, and this was the first paper that my student did. Where we saw for fission gives an effect of 1%,
Well,
but for subbarrier fusion gives an effect of 15%
15.
for carbon-carbon actually, and it decreases. So to answering the question the lady asked me before, maybe if I add the virtual pair in this model, it will bring this down to 15%. Vacuum will bring it down from 15%.
What will happen if you normalize your grid to the data above?
So it will go like this. It will go like this, but the peaks here are very high. So still,
How do
it will go. So if I normalize down,
No, anyway, it's like you
No.
decrease by even by 1 order of magnitude. So
Yeah.
you still have those huge peaks which are even
exactly. So
larger.
these are going. If I normalize down, it will go like this, and then
Yeah, still the resonances are there, but above some
w-
entrance curve or like.
I don't see any, why would you
I
think,
don't know.
apart this thing that he was mentioning, I don't see any hindrance, actually.
So now that you have a theoretical support, you should put a name on it, the Catania effect. Determino. Right, you get a name, if you're successful in the future, everybody proves you are right.
I like
You
that
become-
it's the other
you be-
class.
Yeah, you become famous, you have to put a name
Now
on
we're
it.
going to go, you will,
She is already famous, right? You
She's
say?
We know. Okay, so,
okay.
you make her blush.
Hair, blush, you
Uh,
don't know her.
Any other question about, we are very late, half an hour late. Okay, so.
Is the
yeah,
pasta ready?
Yeah, thank you very much, Albert.